And hello, AP Physics students. I'm very excited to talk to you tonight because we are starting to get to the end. This is the beginning of the end of our journey in electromagnetism, what some people think is the toughest part of all of AP Physics. So, chapter 21, the last chapter dealing with electromagnetism, but some say the most important. So here we go. Chapter 21, problem 1. Let's review. In chapter 20, we said that moving charges, currents, right, can make magnetic fields. And we had this right-hand rule thing, right? So moving charges or current can make magnetic fields. Well, what we're going to learn in chapter 21 is it goes the other way. A changing magnetic field can make a current. So this is just the opposite. Now, we don't technically say that changing magnetic fields make a current. The technical name is that changing magnetic fields induce an electromotive force. All right? And we call, when a changing magnetic field induces an EMF, we call this process electromagnetic induction. Okay? And we're going to be studying about Faraday's law of induction, which basically describes how electromagnetic induction occurs. All right? So, a changing magnetic field can make a current. Well, how does it do this? Well, we are going to have to learn about flux in order to do this. Okay? What is magnetic flux? Okay? This is a capital letter, capital Greek letter psi, maybe? Something? And psi sub b is our symbol for magnetic flux. And magnetic flux is the product of a magnetic field times an area times the angle between those. And we'll talk about that in just a second. And this is called magnetic flux. Okay? Now, this is exciting for a number of different reasons. Number one, since we now know what flux is, we can now make a flux capacitor, right? Because we know what flux is and we know what capacitance is. And we can make a flux capacitor so we can travel back in time so long as we have 1.21 gigawatts, right? Okay, actually flux and capacitors don't have a whole lot to do with each other, but that's good science fiction writing. You just take any two random words that don't normally go together and put them together and call it science fiction. Here's what we mean by flux, though. Here I have an area, all right? So let's say maybe it's a loop of wire or some area that I'm dealing with. And here's a magnetic field going through that area. Now, flux, the word flux comes from the Greek word for flow. Think of the magnetic field lines as flowing through this area, okay? You would get the most flow if this area were perfectly perpendicular to the magnetic field. So we want as much magnetic field to go, as many magnetic field lines as we can to go through this area to get the greatest flux. Now, if these were parallel to each other, like if I spun this all the way this way, we wouldn't have any flux, okay? So B is the magnetic field strength, A is the area in meters squared, B is the magnetic field in Tesla, and theta is the angle between the magnetic field lines and a line perpendicular to the area, okay? That's what magnetic flux is, and we're gonna have to know about that. Okay, so once again here, B is magnetic field, and that is measured in Teslas, right? A is the area, and that's measured in meters squared. And theta here is the angle between B and a line perpendicular to the area. Okay? Just like we showed in the drawing. Now we have a special name for the SI unit for magnetic flux, all right? The name for the Tesla times meter squared is called the Weber, okay? And it is abbreviated WB, okay? So a Weber is a magnetic field of 1 Tesla passing perpendicular all the way through an area of 1 meter squared, okay? Okay, so this is magnetic flux, and here's where it's going to come in useful in calculations. Okay, if there is a changing magnetic flux, we can induce an EMF, and the EMF or voltage induced is equal to the number of turns of wire times the rate of change with time of magnetic flux. Okay? So the induced EMF, the voltage that we can make in a coil of wire, is equal to the number of turns of wire that we have in a given area times the change in magnetic flux per change in time. And if you multiply all these units together, you will get an EMF, or all of these come out to be volts. All right. So the ends of the wires that make an area, a voltage will occur across those wires. You'll get a voltage and you'll get a current. All right. So if you change a magnetic field inside a current, you can make a magnetic field inside a wire. You can make a current flow through that wire. And Lenz's law gives the direction of this current. All right, and Lenz's law is basically this little negative sign here. And Lenz's law says when you induce a current, when you have a changing magnetic field that makes a current, produces the EMF and makes a current, the current produced by an induced EMF moves in a direction so that the magnetic field caused by that current opposes the original change in flux. And this is a lot of words to basically describe whether a current goes around a coil one way or around a coil another way when I introduce a magnetic field. And we're going to save that for a class demonstration. Okay, that was a lot of information. Let's do problem number 1. Okay? Problem number 1 states that I start with a coil, and this coil initially has a flux of negative 50 Webers, okay? And we are going to change the direction of the magnetic field going through this coil of wire, and at some time later, we are going to have a flux of 38 Webers. Now, the time over which this change occurs is 0.42 seconds, and this area that the coil is on only has one coil. All right, so just one loop of wire. All right, so according to our formula for electromagnetic induction, sometimes called Faraday's law of induction, all right, this is Faraday's law here. Faraday's law is this guy here, right? Okay, so Faraday's law states that at the end of these wires, we will get an EMF, an induced EMF, a voltage of -1, all right, times the change in flux is final flux minus initial flux. All right, so I have 38 Webers minus 50 Webers divided by 0.42 seconds. And if I plug that into my calculator, I get an answer of 420 volts. Okay? So if I were to change the flux going through a coil of wire, and I were to change that flux from 38 Webers to 50 Webers in about half a second, I would actually get 420 volts induced across that coil. Okay, nice work, AP Physics students. Like I say, we'll be practicing this a lot in class. Mr. Kirsten, this video was really hard, and it took me 10 minutes of time to learn it. Is there any way we could make this easier? Well, I'm glad you asked, because in this month's Discover magazine, do you guys remember in the Matrix where Neo got like lessons downloaded directly into his brain? All right, and you might be thinking, Mr. Kirsten, isn't that what I'm doing now? Downloading your voice and your lectures and your examples right into my brain? Yes, it is, but what if we could do that directly like Neo does? Wouldn't that be cool? Well, as it turns out, that may not just be science fiction. And if you're interested in how neural patterns and sleep and sci-fi science fiction is actually leading to us downloading stuff directly into our brain, you should check out this month's issue of Discover Magazine. And that is our cool thought for today. So, nice work, AP Physics students. We will see you in class tomorrow. Okay.